So in machine learning, one technique that has become incredibly popular is called stochastic gradient descent. And the rationale for stochastic gradient descent is the following. Very often, what you try to optimize in machine learning is not just the classifier. We're trying to find the classifier that minimizes certain loss. In which case, the function that you have to minimize is the loss function itself. And there are many situations where the loss function takes on a very specific form, which is a sum from I equal 1 to n of Li of theta, where Li of theta is the loss that you incur at a specific point in your data set, meaning it's a function of xi, yi, and theta, but it only depends on the sample I and theta. It doesn't depend on the other samples j in your data set. In a way, it says that the function here is somewhat separable across the different samples. And that specific form suggests that we can approach the problem of finding the minimum in a slightly different way. So if you write the gradient of your L of theta, your loss function that you're trying to minimize, as a sum from I equal 1 to n of the gradient of the Li of theta, that's just by linearity of the gradient, then you see that your gradient descent update takes that specific form where you're saying theta j plus 1, your next candidate for the value of theta is going to be theta j minus step size eta and the gradient, which here has that form. And it's problematic if you have a huge data set, because that sum here can be extremely large. Okay, so that's very expensive to compute this. If n is much, much larger than 1, you have a huge data set, or worse, if you cannot have all the data. One thing you should realize is that machine learning, at least its modern form, has really embraced big data. Data sets, it's very common if they're not toy data set, they have millions, if not tens of millions of picture vectors that you can play with. And one very real challenge that you have is, even though you might be able to write the gradient, even though you might be able to even compute it on a sheet of paper in principle, all that data does not fit in your memory. If it doesn't fit in your memory, you can compute it. So it's as if you are missing data. And therefore, that expression that looks like nothing is actually very hard to compute just because of constraints that you have in your actual system on your computer. And instead, what stochastic gradient descent is saying is it's saying, well, maybe let me not try to compute the true gradient, because that's very expensive. Let me instead estimate the true gradient by simply looking at the gradient at the point xi, which is what I call the gradient Li of theta. So this is not the true gradient. Okay, so one thing to be clear, this is not the true gradient, because you're missing a whole lot of terms, but your hope is that maybe that will be a good approximation of the gradient, and that by iterating here, you will eventually get the same result. The reason it's called stochastic gradient descent is that one can show under some assumption that this grade, nabla Li of theta is indeed an estimator of the true gradient, and its expected value is a true gradient, but its realization might be different. And so there is some stochasticity, there is some noise in the process here, and therefore we expect that this might not be quite as powerful or quite converging as fast as the regular gradient descent, but the benefit that you have is that you gain a lot in terms of complexity. What's interesting is that you can actually prove that that algorithm, again, there's some conditions that are a bit restrictive in terms of having a function that is convex, something that is Lipschitz, that kind of qualifies how fast the function can grow. You can prove that stochastic gradient descent actually still does pretty well. And therefore, there is very serious theoretical backing to justify why these sort of updates, even though they are not the ideal updates of gradient descent, would actually still work extremely well. I will add some notes on the detailed proofs as to why that would work. And what you will find in machine learning literature, especially people who use it as a tool to optimize, say, a neural net, is a variation of stochastic gradient descent. People have a specific jargon and lingo to talk about this. The vanilla flavor of the gradient descent, when you include all the points from 1 to n, is called batch gradient descent. It really means that you're taking all your data as a batch and computing the gradient based on this. If you choose to select a subset of the points to compute your gradient. You call that a mini batch. And the stochastic gradient descent, the way I described it, corresponds to a mini batch of size 1. And you have variations of that called AdaGrad, RMSProp, Adam, which are all geared at one thing. They're all geared at saying, let's embrace this idea of gradient descent, stochastic gradient descent, with an approximation of the true gradient. But let's try to be a bit smart about how we choose that step size. And in particular, can we come up with a smart rule that does not involve us computing the Hessian, because we know that's expensive, but a smart rule that maybe only depends on first order gradient still, that will allow us to choose the step size adaptively. And I think Adam is by now almost a default optimizer that you would use if you were to train a neural net, is doing exactly that kind of things. So I will try to at least give you a reference and pointers to all these different optimizers. What's interesting is the following. Proving that these variations actually converge to the right thing under some condition, that's really hard. But using them is much easier. And if you were working at Google a few years back, you could actually invent AdaGrad over a summer internship and have a paper that is cited 12,000 times. Now, I think that time is long past gone. If you want cited 12,000 times, you have to do a bit more. But it shows you how, people in machine learning got really interested again in all these optimization algorithms because they were desperate to come up with efficient algorithms to minimize loss functions in situations that were very specific to machine learning, where you had these separable functions, and in situations where you had so much data that you could not store everything into your computer. And the one thing to remember, that's what I wanted to highlight in this part of the lecture, is that you have to give up coming up with nice closed form expression for all these things. In machine learning, usually you don't have closed form expressions. All you care is having an algorithm. Maybe you're lucky and you can prove that your algorithm converges. More often than not, you don't even have the properties on your function that allow you to prove anything. And yet, what's a bit surprising is that these algorithms, such as stochastic gradient descent, are extremely powerful. They tend to work extremely well, even in situations where your functions are non-convex. And that's why they're used virtually everywhere as the machinery, if you wish, behind the machine learning algorithm.